th century, Antoine Lavoisier introduced the idea of mass conservation in chemical reactions. 19th century, Julius Robert Mayer and Hermann von Helmholtz applied mass conservation to material flows in open systems. Industrial Revolution, mass balance began to be used systematically in industries like mining and metallurgy. Early 1900s, chemical engineering pioneers Arthur D. Little, William H. Walker, and Warren K. Lewis emphasized mass balance in process design. Mid-20th century, mass balance applied in continuous processes, especially petrochemicals, with control theory enhancing stability and safety. Modern day, software like Aspen Plus and MATLAB are essential for mass balance in environmental and biochemical engineering. Late 18th century, James Watt's improvements to the steam engines sparked interest in concepts of work and heat. Mid-19th century, the first law of thermodynamics was established, stating that energy cannot be created or destroyed, only transformed. J.R. Mayer and Hermann von Helmholtz. Mayer applied the first law to chemical reactions, while Helmholtz explored general energy conservation. Early 20th century, when chemical engineering became an official discipline, energy balance was applied to open systems. Unit operation method pioneers like Arthur D. Little, William H. Walker, and Warren K. Lewis used energy balance in process design, breaking down complex processes into segments. Late 20th century, software like Aspen Plus and MATLAB enabled more precise energy balance calculations in fields like environmental and biochemical engineering. Contributors, Mayer, Helmholtz, Little, Walker, and Lewis contributed significantly to the development of energy concepts in chemical engineering, later enhanced by control theorists and software for real-time monitoring and advanced simulation. Mass balance for open system. Application of conservation of mass to the analysis of the physical system. For an open system, mass balance involves tracking the inflow, outflow, and accumulation of mass. It is based on the law of conservation of mass. The law of conservation of mass states that mass cannot be created or destroyed. Mass balance equation for open system. Taking cross-section of the reactor, rate of accumulation mass in system is equal to total mass entering system minus the total mass leaving system. Note that flow into the system indicates positive signs and flow out the system indicates negative signs. The first equation is transient state of open system. The second equation is for steady state of open system. Energy balance for open system. Energy balance is the principle that the total energy entering a system must equal the total energy leaving the system plus any accumulation of energy within the system. This concept applies to both open and closed systems in thermodynamics and engineering, where different forms of energy such as heat, work, kinetic, potential, and internal energy are accounted for. Law of conservation of energy is the first law of thermodynamic. The primary types of energy to consider in an open system are internal energy, kinetic energy, and potential energy. Energy balance equation for open system. These are the type of energy equation related to energy balance in open system. Next, total energy entering the system is equal to the total energy leaving the system. Note that flow into the system indicates positive sign and flow out the system indicates negative sign. The equation shown in the black box is expanded steady-state open system equation, taking the cross-section of the reactor with turbine and heating bar. The general energy balance equation for an open system shows that the rate of energy entering, plus any heat or work added, minus the energy exiting, equals the rate of energy accumulation. This helps track energy flow over time. In open systems, work has two components, which is shaft work and flow work. The flow work is given by where m is mass flow rate and PV represents pressure and specific volume. Equations 4 and 5 provide a more formalized energy balance for input and output streams. Equation 4 accounts for the total energy of all inputs and heat added, minus the energy of outputs, to represent the rate of energy change within the system. Equation 5 breaks down the energy into terms of enthalpy, kinetic energy, and potential energy, offering a clearer view of how each energy form contributes to the system's overall energy balance. By substituting the definition of flow work into equation 5, the equation now includes energy terms for both the input and output streams, including internal energy, kinetic energy, and potential energy, along with heat, added, and any other work. Next, we apply the enthalpy definition, which combines internal energy and flow work, by substituting enthalpy in place of internal energy. For a steady-state system, there's no accumulation of energy over time, so the rate of change of stored energy becomes zero. Finally, by incorporating both the enthalpy definition and the steady-state condition, we arrive at the simplified energy balance for an open system, known as equation 6. This final equation provides a clear framework for analyzing energy flow in open systems. Example question, 500 kg per hour of the steam driver turbine. The steam enters the turbine at 44 atm and 450 degrees Celsius at a linear velocity of 60 meter per second and leaves at a 0.5 meter below the turbine inlet atmospheric pressure and a velocity of 360 meter per second. The turbine delivers shaft work at a rate of 70 kilowatt, and the heat lost from the turbine is estimated to be 10 power of 4 kilocalories per hour. Calculate the specific enthalpy change associated with the process. Here are the solution using MATLAB. For mass balance, in steady state mass flow rate on input is equal to output. For energy balance, enthalpy change is equal to heat plus work minus kinetic energy minus potential energy. Continue on following the heat equation. The final answer obtained is negative 650.6330 kJ per kg. Thank you so much for all of your attention. Goodbye.